There is a update.
Oh, no, thank you.
Still something.
Still something?
Yeah.
On the left.
It's like
Here? No. What? We're starting a buyer scan, whether you want it or not. Are we running there? Yeah. Okay, continuing on with the quasi-chemical model, now going into positive deviations. So we have the Bragg-Williams model, which is the random mixing model, in which the enthalpy, actually the enthalpy change in the Bragg-Williams model is also due to the change in the nearest neighbor pairs. It's just that the number of nearest neighbor pairs is always given by the random mixing model. Quasi-chemical model, the energy is given by the enthalpy of mixing is given by the energy of this reaction, but this also affects the entropy. As this becomes more negative, it shifts this thing to the right. Now we've been talking so far about negative deviations in which this thing is shifted to the right. You tend to have clustering, AB, ordering, not clustering, ordering, AB pairs are favored. Then I said, well, we talked yesterday about how one way of problem with the quasi-chemical model was Z equals 2. It's only, the entropy term is only precise, it's only rigorous if Z equals 2. If you let Z equals 2, however, the peaks are too sharp for reasons which we discussed. I said two ways around this. One way is to write the heat as a mixture of a quasi-chemical and a Bragg-Williams term. So this is the number of AB pairs, and this is the XA-XB, which is considered the number of second, third, and fourth nearest neighbor pairs, where the heat is given by a mixture of two terms, but the equilibrium constant, which affects the entropy, depends only on the quasi-chemical term. So if the Bragg-Williams term becomes very important, then you get a random mixture. If the Bragg-Williams pair is less and less important, you get more and more. So that's one way to fix it up. Another way to fix it up is to not put in this term, but to artificially change the Z here to higher values, which also gives you about the same effect, but does have the problem that you can then run into entropies, which can become somewhat negative and so on. Okay. So now we only talked so far about negative negative deviations. Let's say now, say we have now positive deviations. So let's say that in fact you have positive heats of mixing. In that case, the Bragg-Williams model, of course, gives you if you just have a Bragg-Williams model, then you have AB pairs, which are positive, and that causes a demixing. In the quasi-chemical model, at the same time, this reaction is now shifted to the left, and you have clustering. That is, the number of AB pairs is less than the random value. Okay, and you end up with a cluster. And this should be, then, we would hope, better. By the way, the associate model does not predict positive deviations at all. The associate model works in the binary solutions if you have very strong negative deviations. But of course, even if omega for this reaction is plus infinity, then you just end up with a regular solution. You never really do positive deviations properly with a clustering model. Okay, so let's go down to number 29. Okay, short-range ordering with positive deviations from ideality. Okay, the Bragg-Williams model gives you miscibility gaps, which are, I say, often too rounded, almost always too rounded. So you always find this when you're looking at the Bragg-Williams model. So just was here an example. This is the dots are experimental points. This is the gallium lead system. It has positive deviations, so you have two liquid phase. So I'm trying to fix this with the Bragg-Williams model. So the first one here, there's no quasi-chemical. I said no this is just strictly Bragg-Williams, and I make it a subregular. Okay, the Bragg-Williams term is 14.3, right? Simplified negative here to shift it a little bit to this side. And these are two fits I did with the Bragg-Williams. One fit, what I did was with the Bragg-Williams, I chose the two parameters. These two parameters were chosen, these two parameters, 14.39 and 2.1, were chosen to fit the composition and temperature of the maximum point. and then you see what you get. You get a gap that is basically too narrow. The second case, 17, 15, and 2.5, were chosen to fit the two ends here, the two ends of the miscibility gap at the monotectic to fit this composition and this composition, so they come in directly here, but now you see it's much too high. And the reason for this is that it doesn't take account of the clustering. The Bragg-Williams says that it always remains random. So the only reason that you get positive deviations is because you're forming AB pairs which have more positive energy. But the number of AB pairs is always 2xAxB. In actual fact, the number of AB pairs will be less than 2xAxB because the thing will go this way. Okay, the liquid will lower its Gibbs energy. In the Bragg-Williams model, you're fixing the entropy as to be the ideal. You're not allowing the system to adjust its entropy. In the quasi-chemical model, the system will always try to find internally the internal structure which minimizes the total Gibbs energy. In the Bragg-Williams model, you're artificially not permitting it to change its entropy, to change its distribution. If in the quasi-chemical model you permit it to change the distribution, which you're doing, you're permitting it to shift this way, the effect must be to lower the Gibbs energy of the liquid, because the liquid will then choose the entropy which lowers its Gibbs energy. If the random mixture were the minimum Gibbs energy, then that's what it would do. So this lowers the miscibility gap. And this is always the case. So the result is, well, every time you do a Bragg-Williams fit, you get too high a miscibility gap. Now, of course, you can lower it down by putting in more terms. You can take your polynomial expansion and you can put in a square term and a cube term and a quadratic term, and you can force the thing to fit. Okay? But you have to force it to fit. In many systems, you don't have it at the top of the miscibility gap. In many systems has not been measured. You might have some points here, you might have some points here, but you don't, the top of the gaps are harder to measure and they go up to higher temperatures. So often what you will find is, let's say in this system, there only, as in many systems, there are a couple of points measured near the monotectic to give you this end of the gap at lower temperature, and to give you this end of the gap. So you fit those two ends up quite nicely using a Bragg-Williams model. You're going to predict a top that's much too high. You're not going to get any good prediction. And many gaps you see that have been done in the literature with optimizations, a few points have been measured here, a few points have been measured here, they're fitted up nicely with two terms, and then the top of the gap is estimated, and it's way, way too high. By way too high, it's hundreds of degrees. So it's not trivial. Okay, so with quasi-chemical model with Z is 2, and Ohma quasi-chemical model is greater than 0, positive deviations are predicted, but a miscibility never results. This is rather interesting. So if you take the quasi-chemical model, and let's say you calculate a phase diagram with the quasi-chemical model and you start putting in greater and greater positive deviations. Okay, let's say this is your ideal solution with omega quasi-chemical model is 0. You make it positive, you start to get, the positive deviations make the liquidus come out flat. And as you put in more positive deviations, the liquidus comes out flatter. If you put in infinite positive deviations, the liquid will come out to be perfectly flat, but you will never get an immiscibility gap if you work out the equations. This is quite fascinating. So this is just the Gibbs energy of mixing, just to show you. This is the Gibbs energy of mixing with Z equals 2 for a hypothetical solution with positive values of omega. So I've taken positive values of omega, and as I increase them, the Gibbs energy of mixing becomes, as you expect, more and more positive. But in order to get a miscibility gap, it has to give a thing like this. And it doesn't. With minus 100 joules, it's this, and with infinity, you get a dead, nice, flat. Isn't that interesting? Okay, the legend is that Ising, who developed the Ising model, he was trying to explain, so the quasi-chemical model was Z is 2, that's the Ising model. 1930s, he was getting his PhD at the Université Libre de Bruxelles, and he was trying to explain the formation of domains in ferromagnetic materials. It's a similar thing with the paired spins up and down. And everything worked nicely, except he could never get the immiscibility with the Z is 2, and he never quite understood this, and apparently he just about failed the thesis, and nobody really liked the model, and he kind of gave up science and became a used car salesman. What they said in Brussels. But then people continued on with the Ising model, and Onsager put it into 2 dimensions, in which in 2 dimensions you do get the miscibility gap. And Onsager won a Nobel Prize for this, among other things. And the legend is that one day, 15 years after he abandoned science, Ising was sitting in his breakfast room reading the paper one morning, and he reads that Onsager wins Nobel Prize for the development of the Ising model. Anyway, well, that's the story. But the why don't you get it? And the thing is, the idea between a cluster, it's still, I've had discussions with people about this one, not everybody. This is what it happens mathematically. What does this actually mean? Okay, with Z equals 2, you have a linear lattice, a necklace. And what you'll do is, if you work out here the actual size, you may end up with omega very positive. If omega is very positive, you're going to have long, long lines of A and long, long lines of B, but these never become 2 separate phases. And the number of AB bonds goes slowly down to 0. The number of AB bonds is only between the ends of long, long strings of A's and B's. And you never have any tendency to separate. The Gibbs energy just goes down smoothly like this. It never actually separates, because the number of AB bonds becomes very, very small. Only among the ends of these very long chains do you form these AB bonds, and it's just, these are not separate phases. They're just bigger and bigger clusters within one single phase, and there's never any tendency to split the thing up. Whereas if you have a Bragg-Williams model, even in a one-dimensional model, so what's happening basically, you're decreasing the number of AB bonds smoothly, and there eventually, as omega becomes very large, the number of AB bonds just sort of smoothly goes down to 0, and you never get a bump in the middle. It's always better to have a little bit of entropy in the middle that comes down that way. If you do the Bragg-Williams model, you have a random mixture. The number of AB bonds is always 2xa xb. And so this then gives you, because you can't, even though you got a very large positive deviation, the number of AB bonds can't decrease. And so the system then lowers its Gibbs energy by actually splitting into a large area of A's and a large area of B's. Okay, so the Bragg-Williams model gives you the miscibility gap, but it doesn't take account of the clustering, and therefore it gives you too big a miscibility gap. The quasi-chemical model with Z equals 2 takes care of the clustering, but it doesn't give you the miscibility gap. So what do? Well, we could try to use Onsager's equation or something. Well, one thing we do is, we could use Onsager's equation and try to fix this thing up in 2 dimensions and 3 dimensions. But we don't want to do that because it's too bloody complicated in 2 dimensions, and you can't do it in 3 dimensions. You might ask then, well, why with the quasi-chemical model and clustering? And this is the question that I've argued with theoreticians about. Okay, so if we do the quasi-chemical model, say we do the quasi-chemical model, okay, if you do the quasi-chemical model with Z equals 6 using the approximate equation, then you get a miscibility gap. Or with Z anything greater than 2, 2.001, you get a miscibility gap. So any value of Z greater than 2 with the quasi-chemical model, you will get a miscibility gap. The higher the value of Z, the closer, of course, you come to the Bragg-Williams. If Z equals infinity, it reduces to the Bragg-Williams. Okay, now the question was, well, is this just an artifact of the entropy equation? The entropy equation that we use in quasi-chemical model is approximate, as Z is not equal to 2. So is this simply because is this an artifact of the approximation? In other words, the question was, if we used the real Onsager equation, the proper equation with Z equals 6 or 12 in 3 dimensions, would that then give us a miscibility gap? Or would the quasi-chemical model never give you a miscibility gap if you did it correctly, if you had the proper equation? The answer is, it would give you a miscibility gap. Apparently, I've heard the Onsager thing has been worked out. It gives you a miscibility gap. Also, they have done this sort of thing using molecular dynamics, where you actually simulate a liquid in 3 dimensions, and the only energies are the pair energies. Okay, and then you set Z equal greater than 2. You have only the pair energies, and you see, will the thing separate into 2 phases, and it does. So the quasi-chemical model assumes that you have only pair energies. Okay, and you have only pair energies, pairs that randomly distribute themselves, and yes, you do. So it's not an artifact of the approximate equation we're using with Z equals greater than 2. It's the quasi-chemical model with Z greater than 2 in 2 and 3 dimensions does in fact give you miscibility. But why is this then? Why, like physically? And it would seem to me that in 1 dimension, these are your groups, and your groups are only joined by AB bonds at the ends. So the number of AB bonds is extremely small, whereas in 2 and 3 dimensions you can end up with domains. These domains are, say, rich in A, these domains are rich in B, and there's a lot of AB bonds between the 3-dimensional domains. Okay, so the number of AB bonds can remain higher. This is not totally satisfying to me either, but I think it has something to do with that. We could discuss that, but anyway, the point is that with Z equals 2, mathematically you do not get the miscibility gap, but with Z equals 6, doing it correctly, or with molecular dynamics, or Z is greater than 2, you do in fact get the miscibility, and you also get it with the approximate equation. So there are 2 ways of getting a miscibility. One is to then have Z is greater than 2. The other is to keep Z equals 2, but to add a Bragg-Williams term, because the Bragg-Williams term. So both the ways that I said with the negative deviations for making the peak less sharp also work for giving you the miscibility gap. And the positive deviations, that is, we can either make Z greater than 2, or we can add a Bragg-Williams term. So with the proper choice of a Bragg-Williams to quasi-chemical ratio with Z or 2, or alternatively with the proper choice of Z with omega 0, flattened miscibility gaps can be produced, which are in good agreement with measurements, even with 1 or 2 terms. So okay, so here's the same system. The solid line here then was obtained with the big solid line was obtained with a quasi-chemical term, and with a Bragg-Williams term ratio of 1 to 7. Z is 2. So you don't have a lot of Bragg-Williams, it's 1 part in 7, and then you get a pretty nice fit. Or the other way of doing it is not to use a Bragg-Williams. Here I've used Z as 3, and I get a reasonable fit to the thing too. So once again, you're basically just adding 1 parameter. I keep the Bragg-Williams term to be the same, just a ratio. Now you get a fit. So this is what you have to do if you want to fit miscibility gaps properly. If you fit them directly with Bragg-Williams, you get too big a gap. You either got to add a Bragg-Williams term in your quasi-chemical, or you can lose higher values of Z. And we're finding that the Z's, or you can do both if you want, they tend to need to have smaller values of Z than we knew sometime for negative deviations. Because Z, as I say, this whole thing comes down to the mathematical approximation of the entropy. And this would be the heat of mixing as well. They're in the same system. These are the measured enthalpies of mixing, calorimetric enthalpies of mixing, measured, 2 different authors, and these are calculated using the two equations that I had here. Now this is important because fitting this gives miscibility gap. I fitted the miscibility gap with these two equations, but that just fits the Gibbs energy. The question is, are you simultaneously fitting the heat and the Gibbs energy and the entropy, or are you just fitting the Gibbs energy? Well, in this 4 systems, there are not too many, but systems in which heats of mixing have been measured, we're fitting the heats of mixing as well, which means the entropy. This shows the heat of mixing is correct. The phase diagram shows the Gibbs energy is correct, so the entropy must be correct. Now the other thing we found, remember we said here you have an AB system. Remember when previously we had an AB system. Well, let's if we had an AB system, say these two systems are ideal, here we had an AB system with strong negative deviations here, then this gave you positive deviations along here. Okay, if you now have a system with positive deviations along, so this is the miscibility gap. So this is the AB system. These 2 points here are the end of the miscibility gap in the miscibility of the monotectic. Okay, if this point here and this point here are the end of the miscibility gap. And if you then project this out into the ternary system, you get this, the two-phase boundary comes out like this. The miscibility gap comes down, of course, it ends down here, but there's like a dome comes up here and comes down. How far out that dome projects towards C, again, depends upon the ratios here. If the omega Bragg-Williams, it's the same thing. The omega Bragg-Williams gives you the biggest miscibility gap. It also gives you the biggest projection out into the ternary system. Okay, generally overdoing, well, almost always overdoing it. If you just use a Bragg-Williams, not only do you get too high a miscibility gap in temperature in the binary system, but then when you do the ternary system, it goes too far. The gap doesn't come down fast enough. Okay, and if you go down towards the quasi-chemical model, the gap becomes smaller as you go in. And the same thing, did I show it here? No. Well, the same thing, of course, would be with Z. If you're using higher values of Z, it's more like the Bragg-Williams. Smaller values of Z bring it back in. So, the Bragg-Williams model doesn't give you good fits to the miscibility gaps. The quasi-chemical model does, but you do have to play with the either the value of Z or with the ratio omega Bragg-Williams to omega quasi-chemical. However, we've tried to make this, we're writing up a couple of papers on it. Supposed to have been writing one up for the last year. Showing, however, that you can, in a series of systems, you can find pretty much a trend. So you take a whole pile of systems and you use the same ratio in all the systems, pretty much, or you use the same value of Z for all those systems. So it isn't quite as bad as it looks. You don't have to guess every system. Generally, if we get the right value, the value of omega, either the ratio or the value of Z that we use that gives you the best fit in the binary, also gives you the best fit out here. So anyway, that is the... It's a shame we can't do the quasi-chemical model with the entropy term correct, because then I think it would work out correctly. But maybe even then it wouldn't, because the quasi-chemical model is not properly taking into account second, third, fourth. It's only about. So you might still have to put in the Bragg-Williams term for the higher order terms. Now we can talk a little bit later about the quasi-chemical model is the clustering model, is the cluster variation method in the pair approximation. Bragg-Williams is called the point approximation because you're distributing atoms on points. The pair approximation is distributing pairs on pair sites. You can go to higher orders. You can consider quadruplets, groups of 4 atoms or 6 atoms arranged on different sites. And there's a cluster variation method, which I'll talk about a bit later. The trouble is you rapidly get way too many variables, way too many things to try to fit. You get huge numbers of components, and also I think you're taking the concept too far. I mean, you can push some of these a model cannot be pushed too far. You start taking the thing too literally. Once you start talking about atoms, 6 and 8 atom groupings and so on, you're fooling yourself. But anyway, we'll talk about that later. Anyway, so that is the quasi-chemical model that's the quasi-chemical model. Now, that was the quasi-chemical model non-rigorously in this number 14. Okay, now I want to go to number 17 here, which is the paper we published, the first paper we published on the quasi-chemical model binary, and basically nothing has changed since this was published in 2001. Okay, this performed a okay. Whoops. Suppose it's full screen. All right. So this is the notation that we use now. You can go back to that paper I had before, number 16 or something, 1984. We changed the notation slightly since then. Okay. So I'm going to go through the quasi-chemical model and the binary solutions. Okay. So this is the way. Here's your pair. These are your pairs. And we call the energy for that delta G AB now. So delta G AB is the Gibbs energy change for this per mole of pairs. Okay. So for 2 moles of AB pairs, delta G is the energy per 2 moles of AB pairs. You've got to be careful sometimes if you're talking about, when you're applying the model, is this the energy per mole of pairs or the energy per mole of AB? So it's energy per mole of pairs. So there's been a minor change in the original formulation. We let omega minus A to T be the energy per mole of components. Now it's energy per 2 moles of pairs. Na and Nb are the number of moles of A and B. Nij are the number of moles of pairs. Za and Zb are the coordination numbers of A and B, which we're assuming for the moment to be independent of composition. Okay, then this is your quasi-chemical mass balance. This is the number of pairs emanating from the central A, and that has to be equal to twice the number of AA pairs plus the number of AB pairs by a mass balance. Same for the B. This Za and Zb can only be different from each other in a liquid. In a solid solution, Za must equal Zb because you have a rigid lattice. Okay, we also introduce pair fractions, Xij, which are the fraction of all pairs out of the Ij pairs. And of course the overall site fractions are, the overall mole fractions or site fractions. Xa and Xb are the number of site. And we introduce now something called coordination equivalent fractions. And Ya is equal to, it's the mole fraction, Na over Na plus Nb, but weighted with respect to the coordination numbers. Now if Za equals Zb, then Ya and Yb are just the mole fractions. Okay, if Za equals Zb, the Z's all cancel out here. Okay, so the Y's are the mole fractions if Za equals Zb, the as in a solid, but we can weight them with respect to the coordination numbers. I call them coordination equivalent fractions because in molten salt chemistry you talk about charge equivalent fractions. So I wanted to distinguish that. So doing the mass, substituting 2 and 3 into 4 and 6 then rewrites the mass balance this way, and you can verify that yourself. This is just mathematics, so Ya and Yb are equal to this. If Za equals Zb, then this is Xa and this is Xb. So fraction of A, total overall A is the fraction of A pairs plus the fraction of AB pairs over 2. The Gibbs energy of the solution is then given by, well, the mixture, mechanical mixture of the two components, where G naught A and G naught B are the pure energy components, minus T delta S configurational, plus the number of AB pairs over 2 times delta GAB. This is assuming strict quasi-chemical, no Bragg-Williams has been added. Okay, the configurational entropy then is given by the expression I showed. You don't have to put a Z in here because this is, I'm not doing this per mole. This is a number of mole. This is the total extensive delta S, not delta S molar, it's the delta S for the solution. So this is the, you have NAA pairs, and this is what I said. So NAA log XAA plus NBB log XBB divided by the values in an ideal solution, and dividing by YA squared, YB squared, YA, YB, and then adding in the ideal term so that it comes in correctly at 0. You might say Y is a number. Okay, when we did this, when ZA equals ZB, then YA equals XA and YB equals XB, and YA squared is XA squared, the number of AA pairs. When ZA is not equal ZB, why would I divide by YA squared? So I have to prove that that's the number of AA pairs when ZA does not equal ZB. Okay, so we continue on here. So as I said, because no exact expression is known, it's an approximate equation. However, it can be shown to be an exact expression for one-dimensional lattice. Furthermore, when delta GAB equal to 0, then A and B should be randomly distributed over the quasi-lattice sites. That is, XAA is up to YXA squared, so in an ideal solution you'd get this when delta JB. The second term on the right of equation 10, to derive equation 11, consider that the total number of moles of pair bonds emanating from the A and B atoms or molecules are ZANA and ZBNB. So you got ZANA coming from the A's and ZBNB. The probability in a random solution that a given pair has both ends emanating from an A is thus equal to ZANA over ZANA plus ZNB squared equals YA squared, and similarly for XBB and XAB. Think about it. This is the total number of pairs you've got, and this is the number of pairs that are coming off at A. Okay, so the total number of pairs coming off in A divided by the total number of pairs squared gives you the probability. And similarly for XBB and XAB. The equilibrium distribution is then calculated by setting dg dNAB equals 0 at constant overall composition, taking into account the mass balances. And that then gives you the equilibrium constant. Okay, which is the ratio of pair fractions, exactly as we had before. This delta GAB, of course, now can be a function of temperature as well. It's a function of temperature, and then if delta GAB is a function of temperature, then it represents the heat, the enthalpy. Delta GAB then is the enthalpy for this reaction minus T times the non-configurational entropy for that reaction. This is the other entropy is the configurational entropy term. Okay, then, for a given value of delta GAB, the solution of equation 13, together with the mass balance equation and so on, gives you NA, A, NB, B, and NB, which can be substituted back, and you can solve the whole thing. If you choose a value of delta GAB, it gives you the mole fractions. Putting them back into the equations, you end up with all the thermodynamic properties for the system. Equation 13 is the equilibrium constant for the quasi-chemical reaction. When delta GAB is 0, equation 13 is satisfied as delta GAB becomes. Okay, so as the delta GAB is 0, you get an ideal solution, and we'll look through all this. The composition of the maximum short-range ordering, the minimum composition here in the entropy and the heat equation, I said, these are heat and entropies for different values. Okay, by the way, another way of looking at this too is that if you replace, if we do the, if we plot the minimum versus x, the mole fraction here, then the minimum can come in different places. Okay, because if it's A2B, it's going to be over here. But replacing x by y, you always have the maximum ordering is always when y is 0.5. That's why we do it that way. So if you plot AB and you use the equivalent fraction, then you always get your minimum at 50%. That's why we do it. That's basically what you're doing. You're shifting. You're making a shift in your definition of your mole of your composition variable in order to put the minimum always at 50%. Okay, the composition of maximum short-range ordering is determined by the ratio ZB over ZA. So if ZB equals ZA, it's 50%. For example, in a liquid nickel-sulfur solution, the maximum short-range ordering occurs at 50%, X sulfur, X nickel, where nickel atoms are predominantly strong and vice versa, hence we said Z nickel equals Z sulfur. In copper-sulfur solutions, on the other hand, the maximum ordering occurs at the composition corresponding to Cu2S, where X sulfur is a third. Hence we said Z sulfur equals 2Z copper, so that Y sulfur equals a half when X sulfur equals a third. Okay, so in pure Cu2S, which is almost completely ordered, every sulfur has twice as many coppers around it. There's twice as many coppers as sulfur, so the coordination of sulfur must be twice that of copper. Okay. If you then were to plot, however, in the copper-sulfur system, if you were to plot copper, sulfur versus the equivalent fraction of sulfur, your minimum would be at 50%. Okay. Okay, in order to permit the model to be useful for fitting data, okay, this is now where we're going beyond what I talked about in the previous slides. Now, with the previous slides, I basically let that delta GAB parameter be constant. Okay, so now your delta GAB parameter is we permit it to vary with composition in exactly the same way as a polynomial, exactly the same way as we take the regular solution and turn it into the polynomial equation. In the regular solution model, you have GXS is XA, XB times a single parameter, which is just a one parameter fit. So to make that better, we say this is A plus B, XB minus XA plus C, XB minus XA squared plus etc. We just make a polynomial expansion of the omitted term. Here now we simply make a polynomial expansion of this delta GAB term. So if we just had one parameter, then we just have the first term. I could write this as the delta GAB, which is your quasi-chemical parameter, is an omega minus an A to AB. So that's assuming it's independent of composition and giving it a temperature dependence. This is your enthalpy, this is your non-configurational entropy. And now we can add a general polynomial term the same way we did here. A sum of omega ij minus a to ij, ya to the I, yb to the j. Okay, this is just a general polynomial. This is exactly the same as we did for the polynomial model. I wrote exactly the same expression. Okay, so these terms then can be, if you have ya to the 1, yb to the 0, this would be omega ab 1, 0, or you could have ya, y to the 0, yb to the 1, and this would be a 0, 1, 0, 1 terms. The 0, I write 0 here, or you can also write 0, 0 if you want. Or maybe I'm wrong, maybe we didn't use the latest bloody notation here. Okay, that's all right. So this is writing it as a general polynomial. Actually, this is not the absolute latest notation. It's pretty close to it. Okay, what about the next paper? Sorry about that. I forgot in the next paper we did introduce a slightly better notation, but it's basically the same thing. We just gave different symbols for these. Okay. Anyway, this is what we got then. So this is your quasi-chemical term, and this is just an polynomial expansion, so that you can do fine-tuning when you're doing your curve fit. And of course you could add a C log t term too if you wanted, and make a delta Cp not 0. You can do that. Alternatively, the expansion could be written using a Redlich-Kister polynomial, yb minus ya, Legendre polynomial, whatever you could do, Redlich-Kister expansion as well. Okay, this is important. The Bragg-Williams approximation, when that delta GAB is small. So I'm trying to show now that the I talked about this before, but the quasi-chemical model reduces to the Bragg-Williams model, approaches the Bragg-Williams model as the delta G term, as the omega, the delta G term approaches 0. As delta G is equal to 0, the system becomes randomly mixed, and the system is an ideal solution. If delta G is small, it's not an ideal solution, but it's very close to being the Bragg-Williams, close to the polynomial model. It reduces to the polynomial model. The total number, so when the total number of pairs in solution is equal to this, is equal to ZA. So when delta GAB is small, NAB is approximately equal to ZANA plus ZBNB2 over 2 YAYB. When NAB is small, when delta GAB is small, you have a very, very nearly ideal solution, and this is the total number of pairs. If ZA is equal to ZB, then this is just the total number of moles, but this weights it. In this case, it is approximately equal to the random mixing Bragg-Williams model. Substitution then gives in the Bragg-Williams limit for small delta GAB, if you substitute the approximate expression for NAB back into equation 9, which is your equation here. In equation 9, we're substituting the approximate expression for delta GAB here. We get that the Gibbs energy is equal to roughly this, with an ideal mixing entropy plus this term here times delta GAB, which you can see is a regular solution term. If ZA equals ZB, then this is just equal to the total number of moles times Z over 2, which is what you get in a Bragg-Williams approximation. Remember, the Bragg-Williams approximation, and when we write Bragg-Williams, we write XA, XB, omega, where omega is per mole of solution. But now this delta GAB is per moles of bond, so we'd have to write N total Z over 2 in front of the thing to make it per mole of bonds. This is simply because delta G is per mole of bonds rather than per mole of components. So if you let ZA equal ZB, then this simply becomes N total over 2, N total Z over 2, N total Z over 2, which is the number of pairs of bonds per mole of components. And this is the delta G per mole of bonds. So delta G per mole of bonds times the number of bonds per component, mole of components, gives you the, well, think about it a little bit. This reduces exactly then to the regular solution equation when ZA equals ZB and when you're in the limit. Okay. So what's happening is that as the thing goes down to, as the thing approaches ideality, as delta G becomes smaller and smaller, the distribution becomes ideal, approaches ideality. The NAB approaches simply the 2XAXB, and the whole thing reduces to the polynomial model. Delta GAB then the delta GAB expansion here is the same as the delta GAB expansion we use in the polynomial model. So even the coefficients are the same as long as you account for the NZ over 2 term. And we have found in many cases too, if we sometimes if we have an old system that has been modeled using the polynomial model with small values of omega, and you want to re-optimize it using the quasi-chemical model, you then use exactly the same values of omega, being careful that you correct for the Z, and you'll get almost exactly the same phase diagram, and then you can just adjust the parameters very slightly. Remember, the quasi-chemical model still always, even if omega is small, it always takes into account a little bit of non-randomness, which is better than, because you always have some. But rather than refit the whole, if you have a system and you'd like to refit it, a system that's been fitted with a polynomial, it's not very far from ideality, but you would like to make it a little bit better and fit it with the quasi-chemical model, taking into account ordering. Just put the parameters directly into the quasi-chemical model, correcting for the Z, and look at it, and then just make some small adjustments, positive or negative. Well, you have to generally be positive because the quasi-chemical model. You'll also find if you do that, if you put in the quasi-chemical model, you're always lowering the Gibbs energy a bit. Because you're giving the system more freedom, you're allowing it to play with the entropy, so it will find a way to lower its Gibbs energy. So you have to put in a slight positive term. But generally, you can refit these things in a few minutes by just changing one or two parameters a little bit. Okay, for those who like mathematics, I haven't actually proven that you got to prove something here. I made an assumption. I've assumed that the entropy term goes to 0 faster than the enthalpy term. You see, I've said that when it's small, I said that when delta G is small, NAB is given by the random mixing approximation. So I'm basically assuming that the entropy term has gone to the ideal before the enthalpy term, or goes faster to 0 than the enthalpy term, which is basically what the quasi-chemical, what the Bragg-Williams, what the polynomial or the regular solution model is saying. The regular solution model is saying that as long as GXS is small, you can roughly assume that the entropy is ideal and put it all under the heap. Okay, but is that a good assumption? And I won't go through it here. For a rigorous proof, however, it must be shown that the ratio of the last term in equation 10 to the last term approaches 0 as delta GAB goes to 0. In other words, the the entropy goes to 0 faster than the enthalpy. And if you like to do this, set this equal to this, expand them as a Taylor series, and if you like mathematics, you can show that this really happens. I'm not going to go through the whole proof right here. So capping up, when ZA equals ZB, then YA equals XA, and delta GAB is then equation is the well-known regular solution. If ZA equals ZB, and if delta GAB is expanded as a polynomial, then equation 16 becomes the commonly used expression for the Gibbs energy of a binary solution expressed as a polynomial of the mole fractions. Okay, any questions about this general? This is the general quasi-chemical model. Pretty much. There's another one or two little things to add.
So we still can add Bragg and Williams to this modified.
Yeah, you can. You just put it in. Yeah, I'll talk about that in a little bit. Yeah, you can add, this is the quasi-chemical model though without Bragg-Williams. And you can vary your Zs. Now you can vary Za and Zb, and this is the whole thing worked out with the... Now here's something that I think is important, starting here. When Za does not equal Zb, okay, so I'm talking about Za does not equal Zb, and delta GAB is small and independent of composition. So now this is just like a regular, it's going to be like a regular solution, except Za doesn't equal Zb. Then from equation 16, a plot of GXS over XAZA plus XBZB versus YB will exhibit a minimum near 0.5. I'll go back to that in a moment. Many years ago, Blander plotted curves of GXS over products of equivalent fractions for many common ion binary molten salt systems. He observed that the curves are generally flatter and smoother. Let me check. That doesn't tell you much. Let's say you have a minimum in your GXS function. The minimum is coming somewhere around a third, or it's not at 50% anyway. If your minimum is at 50%, then you say GXS equals XA XB omega, where this is constant. That will give you a minimum at 50%. Let us say that your minimum is not at 50%, when it's moving over towards 1/3. Okay, we're not talking about quasi-chemical, we're talking about using polynomials now. So let us say your minimum, so the 50%, let's say omega is, here we got omega is negative, your minimum would be at 50% if omega were constant. You want to move the minimum over to the left. The way that you normally do this in a polynomial expression is you add in a subregular term. So you call this A plus B, and let's do it in XB minus XA. Let's do it in the Redlich-Kister, it doesn't matter. So we add in a subregular term, and we want to shift it to the left towards A, so we want it to be more negative on the A side, so in that case B would be positive. That was XB minus XA. Okay, and that will shift your peak over. But the problem is it also changes the shape of your peak. Your peak now was kind of parabolic when you just had one term. But now, you see what you've done is you've made it negative on the A side, but now you've made it positive on the B side of 50%. Okay. If we just plot the second term, XB minus XA, let's just plot the second term. I'm going to just plot the second term, which will be XA, XB times B, XB minus XA, just the second term, or that is negative. That second term looks like this. Okay. The first term is a parabola. The second term flips around like this. It's positive. It's negative on the A side and positive on the B side. Okay, so that is going to shift your peak over to the left, but it's going to give it generally the shape then afterwards. The shape is not going to be round, but the shape will be more positive here, and we'll kind of look around like that. Okay, and you can see it's very similar. Remember the other day I talked about a ternary term, x1, x2, x3, and I can say I can give you positive on one side, and even if your term is positive, you can end up with a negative partial. The same thing can happen here. You're trying to move the curve over here, and you end up on this side giving yourself a positive excess Gibbs energy, you can't get around it. And it doesn't matter, you could say, let's make it A plus, let's take that term out and just use a straight, but it's the same thing, you can rearrange, that could be rearranged to it's the same thing. That term still gives you the same affair, because it can be rearranged to a Redlich-Kister, so you don't get around it that way. You use a subregular solution, you shift the peak, but you change the shape of your curve, and often this is not what you really want to do. Sometimes it is what you really want to do. Okay, but this is assuming that, what is this assuming physically? Well, you're assuming that you're having, as I said, the idea of the subregular model is you have the AB pairs, that's the energy of the AB pairs, and then the energy of the forming these AB pairs, this N, Avogadro Z over 2 times, 2 epsilon AB minus epsilon AA minus epsilon BB. You're assuming in the regular solution that these are independent of composition. Now you're assuming they sort of vary linearly with composition. The bond energies vary linearly with composition, and that gives you this second term. But we see there's another reason that you can have a minimum can be shifted. The minimum can be shifted, at least in a liquid here, I'm not talking about a solid, the minimum could be shifted in a liquid because of change of coordination number. Okay, so let's supposing that the bond energies remain more or less constant. And now we're talking about a liquid, and the reason this shifts over to this side is because the ZB is greater than ZA. And if ZB is greater than ZA, okay, the minimum will tend to be on the side in which you have more A's around B's and B's around A's, so you're going to shift the minimum. Okay, now this is what the quasi-chemical model gives you. In the quasi-chemical model, you can shift the minimum from 50%, even though you keep your omega constant. You can keep the omega, just make it constant, and just by making ZB over ZA equal to 2, you have a negative omega, you shift the thing over to the left. Okay, now you can do exactly the same thing then in the Bragg-Williams model, and the limit of a small thing by simply taking the GXS is YA YB times omega. That's all I have to do. GXS is YA YB times omega instead of XA XB times omega. Where I say, let us suppose that ZA equals ZB. ZB is 2ZA. So YB is ZB XB divided by ZA XA plus ZB XB, and YA is ZA XA, which is 1 minus YA. So plotting GXS versus YA YB puts the minimum at 50% in the YB coordinates, and it shifts the minimum in the XB coordinates over to 1/3 as the omega becomes more and more negative. Shifts your minimum. Because you're saying that but it keeps the shape of the curve the same. You don't end up with this change in slope. You end up with simply a rounded curve, but shifted over. Or in other words, if you plot it in coordinates YB, you simply shift your minimum back to 50% in that. And it has been shown in a number of liquid solutions that we can get a nicer fit with just one term or fewer terms to many systems without having this whole problem by replacing the x's by the equivalent fractions. So and this is just in the Bragg-Williams way, because you're using the limiting case of the Bragg-Williams model, but you're using the fact that shifting the peak is being shifted not because the bond energies vary with composition, which gives you this sort of thing, but because the coordination number varies with composition. And this doesn't work in solids, but in many liquids it has been shown that is that's what's happening. Okay, Blander looked at systems like KCl, MgCl2. Okay, you can read that. Anyway, it seems to be because of short-range ordering. So it's an approximate way of taking into account, or the other way of looking at it, doing it, replacing the x's by the y's is a way of taking into account, partially taking into account some short-range ordering the liquid, while still using the Bragg-Williams type of formalism by simply shifting the P. Okay, let's talk about some more complications. We're bringing in more complications now, which are, so I don't think you're probably going to do this, although in some of the older fits and before we developed the quasi-chemical model, in fact, Sage, we tended to do this a lot using equivalent fractions in the Bragg-Williams model, especially for things like liquid salts and so on, because it gave us way of doing it. Now that we use the quasi-chemical model, we use the quasi-chemical model. This tells you something about structures of solutions, I think. Because I think a lot of times when you're seeing part of the trouble that we're trying to fit liquids up using a polynomial model, and you get this problem that you're changing the shape of the curve by putting in your polynomial. A much better way of doing it without having to go to, you can always fix it up eventually by putting in many, many terms in your polynomial. But if you replace your x's by y's, you don't need any more terms. It just takes care of it, which indicates that it probably has physical basis. Okay, following a suggestion by Blander, we propose a further modification to the quasi-chemical model. Namely, the delta G parameter is expressed as a polynomial in the pair fractions rather than in terms of the equivalent fractions. Okay, so here we expanded delta GAB in terms of the equivalent fractions, which become the mole fractions if ZA is equal to ZB. Now we expanded in terms of the pair fractions. So the delta GAB is equal to, we call it the constant term delta G naught AB, plus the number of parameters which I now call GIJ, GI0, and G0I. The G AB, XAA to the I, this is the number of AA pairs, and this is the number of BB pairs. So you can have AB I0 parameters, or you can have 0J parameters. So it's being expanded, but not in terms of the overall component fractions, but in terms of the pair fractions. And this is, you've heard people talk about GUTS model or something. This is a joke I made a long time ago, the Grand Unified Theory of Solutions, and people liked it, so we talked about, this is a GUTS expansion, the other is a polynomial expansion. Okay, what is the advantage to the GUTS expansion? Actually, we tend to use this a great deal now. The advantage of the GUTS expansion is, let's say, what's the example I have here? Example, so let's call the solution AB. And here you have, let's say, AB. And let's say you have very strong ordering around this. So you have your delta G naught AB, the leading term, let's say your omega naught or delta G naught, whatever you want to call it. Your delta G naught AB term here is extremely negative, so delta G naught AB is very negative. So you have very strong ordering. Okay. So what you have here now is on this side, you have mainly AB pairs and BB pairs, but you have hardly any AA pairs. Okay, at this point here, you've got almost only AB pairs. On this side, you got AB pairs because you got an excess B, you've got BB pairs, but hardly any AA pairs. Okay, this equilibrium here, AA plus BB forms 2AB, is shifted very strongly to the right. And over on this side, you have AB pairs and AA pairs, but hardly any BB pairs. Okay. Now you have some experimental data that you're trying to fit. Okay, when you're trying to fit some experimental data, and you say you take the system, you have some experimental data for this system, phase diagrams, enthalpies of mixing, whatever. You may find, you will find in many cases, say you're using a standard polynomial expression here. So you decide that you want to add to the delta G parameter, you enter a term in YA or YB or whatever because you want to fix up something over on this side. You want to make your fit better on this side. But now you mess up the fit on this side because the YA and YB doesn't take into account anything about this. The terms the terms in YA and YB apply over the whole composition ring. So you want to change up something here, and you end up messing up the system over here. A good example of this would be when you're doing your oxide systems in calcium silica, for example. These are very strongly ordered around the Ca2 SiO4 range. And here you've got your phase diagram on this side, admissibility gaps on this side. Quite different chemistry on the two sides. Generally, with only a couple of terms, you can get a pretty nice fit to everything on this side, but over on this side you got a lot of trouble fitting this miscibility gap, and this is the hard side to fit in your optimization. So you start to introduce terms, higher order terms, polynomial terms in YA to the fifth, Y to the fourth, and whatever to try to fit this. And every time you add a term here, you totally mess up what's happened on this side. Okay? Because you got to try to fit the whole thing together. So you go crazy. You're trying to put terms in here, but not. You're trying to do something that affects this side, but doesn't have any effect on this side. Okay, and this happens a lot because we're fitting a lot of systems that have strong ordering. However, in this expression, you see that over on this side, this term here takes account of only the XBB pairs. Okay, so a term here, this G naught J XBB to the J, will have very little effect whatever on this side because there are hardly any XBB pairs. XBB is extremely small over here. So this second term here will have an effect only on this half of the phase diagram. So you can play with these parameters here to make your phase diagram fit on this side and have very little effect over here, and vice versa on the other side. And you'll find it's a lot easier to fit using guts. Plus, this is actually theoretically a bit better when you're going into multi-component systems too, because this is saying that remember when you're talking about when you're doing a polynomial, you're saying the energy of the pairs depends upon the surroundings. So in the polynomial fit, you're saying the energy of your AA bonds depends on the number of A's around it and the number of B's around it. Here you're saying the energy of an AB bond depends on the number of AA pairs around it and the number of BB pairs around it. It's kind of configuration dependent rather than overall composition dependent. I think it makes a little more sense physically. Anyway, we find that you can generally get better fits quicker with fewer parameters and much less trouble, because these parameters you use on one, you fit this parameter first of all to get you more or less where you want the minimum to be. This is your main term, which will be very negative, and then these terms can be used to fit the two sides independently. Now in FactSage you're not limited to using the polynomial fit or the guts fit. If you want, you can mix them up. You can have a guts term plus a polynomial term. There's no reason you can't. You can do it, and there's no reason not to. You can have a term in XAA, XBB plus a Reddish-Gister term if you wish. You can mix them up if you want to. You can just add them on. This is a linear, it's just a linear expansion. That's why we do the guts thing. And I say this presents a significant practical value solutions, and that what I just said is explained here. You could have cross terms. I remember I only put in terms, we only put in terms I0 and 0I. Now, you could also add terms XAA to the I, XBB to the J, where I and J are both greater than 1. You can do this, but we have found that there's no real advantage to it. We've never found any advantage. And they say also, why not have terms with a G term with this XAB to the I, but XAB is equal to 1 minus XAA minus 1. XAA, the fraction of ABs is 1 minus XAA minus XBB, so they're not independent. So again, we found that this is the simplest way of doing it, and we've never really had any occasion. In most places I know, maybe some of my students have done this, will tell you they wanted to use these terms, but FactSage permits you to put in those terms, but this is what you really need. This works on one side. This gives you pretty well everything you want. So that's the guts expansion versus the I'm going into the details of the quasi-chemical model in very detail because that's what you're doing. Okay, let's take a break and then I'm just about finished actually. Take a 10-minute break.
Just
Oh, that's